We're at the point in Chem 242 where we're able to start talking about some very interesting electronic structures for organic molecules. And so we're going to start talking about conjugated dienes. You'll remember that we talked a lot about alkene chemistry, we talked a little bit about alkyne chemistry. It turns out that a lot of those types of chemistry are going to kind of come back in this chapter. But as is usually the case in organic, right, we're going to see a couple of curveballs. What we're trying to do here, just to give you kind of the long-term view, is that we're eventually going to be talking about aromatic systems. These, of course, are not aromatic, but they're kind of taking a step in that direction. So the first thing is to answer is, what is a conjugated diene? Well, if you look at a diene, what is absolutely necessary for it to be conjugated is this double bond, single bond, double bond kind of alternating system there. And so probably I'll have a kind of a little insert here that kind of shows you what the pi cloud looks like. I'm going to try to draw it as a picture, and it's going to probably get ugly here. But if you imagine rotating this thing to the plane of the blackboard, or I should say perpendicular to the plane of the blackboard, so that we essentially are looking straight on this conjugated system, you'll remember that we have these pi orbitals, and I'll draw them in red here. Right? And so there is a pi bond that's represented by these unhybridized p orbitals here. And so you could imagine that there's also some p orbitals over here, and those are also in this kind of sideways overlap, which I'll show like that. The thing is that that single bond in the middle there, in this kind of system, it turns out that there is like a fairly substantial overlap between this pi system right here. So really what we have is not really this isolated system that looks like this, but we kind of have this system that electrons can kind of jump through this kind of, we'll put it as a dash, right, because it's a little bit of weaker. It's not a single bond necessarily, but there is this what's called a delocalized pi network. And this gives some really important changes in terms of reactivity. We're not going to just be seeing that simple door swing that we saw with the alkenes and the alkynes. We're going to be seeing something a little bit more interesting. One thing that you remember that we talked about covalent theory and how that when we invoke resonance, it's just kind of an admission that this covalent bond theory doesn't really work all that well. But what the true picture of this thing looks like is probably best described by molecular orbital theory. And unless you're really interested in that, we're not going to go into that too much because it doesn't really help us that much. And so we're going to kind of stick in covalent bond theory land. We're going to see a lot of different resonance forms, but the true picture really does, it's probably important for you to understand in like a molecular orbital sense that I'm not going to talk too much about, other than to mention that if you're interested, I'll talk more about it. So how are we going to represent this thing? This idea that there is a certain amount of kind of double bond character to this single bond. Well, if you imagine kind of what looks like an ugly looking resonance form here, you'll notice that we could draw something like this, and you'll imagine that this is not really a 50-50 at all, not even close, really. It's really more of like a 98% kind of looks in this form, and then like maybe a 2% contributor in terms of that. But what it does do is it imparts a little bit of double bond character to that that bond. So you're actually going to imagine this picture as representing this kind of like delocalized pi system here. So let's kind of take a look at some of the special reactivity patterns of this thing. If you remember back to alkene chemistry, we talked a bunch about electrophilic addition, and that was that door swing that we saw coming from a double bond. So let's do that from just our most simple of conjugated diene system. Okay, so let's imagine an electrophile. Let's use Br2 just because we talked about that so much when we were doing the alkene additions. So let's show this double bond reacting just like we've seen before. This double bond swings out. The bond between the two bromines breaks. And let's take a glance at this intermediate that is formed. And so to the untrained eye, this looks just like a secondary carbocation, but it actually turns out to be a really special kind of cation, and this is called an allylic carbocation. Just like we talked about the the special delocalized nature around this bond, this also has a delocalized system where there's actually an empty p orbital here that's delocalized with these other two p orbitals, and we can of course show this through a resonance form that looks like this. And so it turns out that this makes this species much more accessible to the reaction than just a normal secondary. In fact, the stability of this system is right around a tertiary carbocation. Right? Usually, if you see allylic systems, in other words, something that is one carbon away from a double bond, that is something that kind of almost adds a degree of substitution to the carbocation, right? So you don't necessarily have to worry about rearrangements the same way you might have to worry about with a simple carbocation involved mechanism, but you do have to worry about the fact that both of these can actually produce products. So you'll remember that in the second step of the mechanism, I'm going to take this arrow away just because that showed us how we got to that resonance form there. That Br minus that's floating around in the system now, oops. That Br minus that's floating around in the system now is going to be able to attack a carbocation just like it would before. That will end up with a product, which we are going to call the 1,2 product. Right? So this is the 1,2 product. The reason we call it the 1,2 product is that we added over 2 carbons that were right next to each other. Right? And so 1, 2, 3, 4. This product over here, which kind of looks like we've rearranged the carbon skeleton a little bit, or at least we've kind of changed the placement of that double bond. I'm going to have to... That Br minus could have just as easily attacked that positive carbon. And in that case, we would end up with a 1,4 bromine addition. Okay, so you'll notice things got a little bit more complicated because of the presence of this other double bond. Of course, I could have started the whole process. I could have gone back to the beginning and showed that double bond reacting as well. That would have ended up with the same exact 1,2 and 1,4 product, but that's not always the case, right? If we put some sort of other substituent out here, you could actually kind of get different 1,2 and 1,4 products, right? And so we'll kind of see that in homework questions and such. One thing that I wanted to make sure that I did, now that we're introducing this concept of 1,2 versus 1,4, is I'm going to show you a potential energy surface. And we're going to see that this, anytime you have a 1,2 product form, this is what's called a kinetic product, right? So a kinetic product or 1,2 product really means the same thing. This 1,4 product is going to be called a thermodynamic product. And by the way, I'm not going to show you examples of this, but if we continued to make this conjugated system longer and longer and longer, what would happen is that we'd get more and more thermodynamic products, right? Because you could, for instance, if you imagined another double bond out here, right, another conjugated double bond, well, you could see this thing, right, go to a resonance form that looks like that. But then if there's another double bond way out there somewhere, you could form another positive charge, right? And so anywhere along that conjugated system, that delocalized system, you would have the opportunity for things like 1,6 products, 1,8 products, et cetera, et cetera, et cetera. Another thing that is probably, I'll just kind of mention in passing here, which I think that I've said in other realms before, is that the more conjugated your system gets, for some reasons having to do with molecular orbital theory that I don't really want to get into, the lambda max, or the UV absorption, gets kind of pushed closer and closer to the visible range, right? In other words, it gets pushed to lower and lower frequencies, or lower and lower energies. And that has to do with the molecular orbital gap between the LUMO and the HOMO orbitals kind of getting smaller and smaller and smaller. And what happens is, if you get a long enough conjugated system, you end up with a bright compound, a visually bright compound, because it'll start to absorb light in the visible part of the spectrum, and therefore will reflect out certain light. So things like beta carotene, right? The reason that carrots are orange is that it has this huge conjugated system. Maybe I'll include even a screenshot of beta carotene. And so the reason that it's so brightly colored is that it's actually absorbing light in the opposite part of the visible part of the spectrum, if that makes any sense. But anyway, ask me about that if it's confusing. Let's take a look at a potential energy surface now, and you'll kind of see why these 1,2 products are called kinetics, and then the 1,4s, 1,6s, etc. are called thermodynamics. So you'll notice I've kind of done something a little bit oddball. We were just talking about the reaction of 1,3-butadiene reacting with Br2. And instead of starting with the starting materials, I'm going to go right to that intermediate that we talked about. And remember, that intermediate could either have been written in one of 2 ways, but I'm going to actually kind of draw it like this to indicate that there's like this delocalized system right here. So really what this is telling us is that there's this little delta posit on both these different carbons. And so this reaction intermediate is truly just a single species, just like we'd expect from resonance. And what I'm going to do is, on the right side here, I'm going to go towards the 1,4 product, and on the left side I'll go through the 1,2 product. And I'll really exaggerate it. It's usually not this exaggerated, but I'll show it this way. So going this way, we're going to end at that 1,2 product, which you remember looks like this. And remember, we called that a kinetic product. And what I'll do here is I'll kind of do just a little tiny little blump, and then I'll only go down to there, right? Whereas on this side, where we're going to go towards that 1,4 or thermodynamic product, what I'm going to do is I'm going to go, woo, boink. And so hopefully doing it that way, oops, I better put thermodynamic on there. So hopefully doing it that way really exaggerates the difference between something that I can use kinetic control for and something I could use thermodynamic control for. So it is typically said that kinetic products are favored, let's write this in blue, kinetic products are favored at low temperatures. And, it really is, all relative, but usually low temperatures, we're talking like minus 78 degrees Celsius and stuff like that. But what you're doing with a kinetic product, it's the one that is formed most quickly, right? But you'll notice that it's formed quickly because it's got this little hill to climb. But the problem is that the potential energy state of this thing is not nearly as low as the thermodynamic product. But the thermodynamic product, of course, has this huge hill to climb energetically. So the reason this is favored at low T, that not at low temperatures, you really don't have any, any energetic dynamics, enough energetic dynamics in the system for an appreciable amount of this stuff to make it over the hill. Some might, but really not that much. So you're going to see this product at low temperatures. Whereas obviously the other side of the game here, the thermodynamic product, is going to be favored at high T. So usually with high T, we're talking 100 degrees Celsius, or if you see something like reflux, right, that indicates that you're boiling something. And so in that case, what you do is you get the thermodynamic, whatever the relative energetics of these two things are, pretending that this guy is like really, really, really much more stable potential energy-wise, you're going to get a lot more of this lower potential energy state product. And I think it is somewhat obvious. With a whole bunch of energy going on in the system, you're really going to pack things with enough energy to make it over that hill. And once they get over that hill, they almost get stuck there, right? In a sense, right? That's kind of an introduction to conjugated dienes. Of course, I could have shown you basically any reaction that we talked about that was an electrophilic addition to an alkene. We could have talked about it here. But like the ones that really we're going to concentrate on are those like Br2 additions or X2 additions, HCl, HBr, things like that. But it turns out every single one of those has this kind of ability to do either a 1,2 or a 1,4. Or if the system is longer and more conjugated system, a longer conjugated system, you can actually open the door to a whole bunch of other 1,6, 1,8, 1,10 products, etc., etc. So that's a little introduction. Hope you enjoyed it.